And RC circuits, as you've had demonstrated before, are time-varying circuits. And we saw that when I set up the capacitor and bulb circuits here a couple days ago. Do you remember that? You hit the button and the bulbs either would slowly come to light or slowly fade off. What you've noticed, I think, in circuits that we were making before is that it appears that we have instantaneous current. As soon as we flip the switch, the current's running in our circuit. As soon as we pull the wire, the current's gone. Did you notice that with the lab you were doing? Well, it's not entirely instantaneous, but it is really fast inside a circuit. Because like I said, if all you have is a resistor and a power source, the electrons are already there. As soon as you push one into the wire, they all start to move. The difference is when you add a capacitor to your circuit. One of the things the capacitor does, it can hold charges. Because it can hold charges, it can take time for things like current to build up, or take time for current to dissipate or disappear. So what we're going to use Kirchhoff's laws, and we're going to study a single RC circuit, which we haven't done yet. We've talked about using Kirchhoff's laws to study a single set of resistors or a set of capacitors, but this is a single RC circuit. Now, we're not going to do anything crazy here, but this is going to involve a little bit of math that might be a little outside some of your capabilities, but you're going to have to catch up to this pretty quick. The one thing I will state that's helpful is that once you've seen this done once, it's going to be the same for every version of this. Now, I'm not saying the setup and the actual integral is the same, but how we act on it's going to be the same. You're going to do the same kind of integral every time. But let's take a look at what this is going to look like, just so we get a start. First, if I want to use Kirchhoff's laws to study this, I'll remind you that Kirchhoff's first law, I think we keep saying law, but it's really just a rule. Kirchhoff's first rule is talks about the sum of the voltage drops being equal to 0. In this circuit, until I close switch A, nothing happens. But when I close switch A, I will have a single loop through my circuit. And Kirchhoff says that in that single loop through the circuit, the sum of the voltage drops will equal 0. Now, if you remember from before, we have expressions for, say, the voltage drop across a resistor and the voltage drop across a capacitor. Those look familiar to you? All right, well, let's go ahead and sub those in. Now, herein lies the problem. Current is defined as the rate at which charge passes through a circuit. We've defined it before as just charge over time. But in a circuit where the current might be changing, it would be the rate that the current flows through the circuit. I do want to say a few things about current. Current is not a vector property, although it has a lot of things that classify it as a vector, meaning that we tend to think that current flows in a single direction through a circuit. So it has vector-like components, but current itself is not a vector. But it has direction inside a circuit. I want you to keep emphasizing that, because we're going to have some stuff in the future where the direction of current is going to matter, but we don't talk about the direction of current as a vector. Okay, we will talk about maybe the direction of the wire as a vector, because remember, current is just the flow of charged particles inside a circuit, but the wire directs the direction of the current. Does that make sense? So you can have a wire that keeps changing direction. The current in that wire will be the same everywhere, but the vector portion of the direction of the flow of charges is dictated by the wire. So we don't state that current is a vector. We just state it's the flow of charged particles inside the wire. Now, the reason I wrote lowercase I and lowercase q in my derivative is because I want you to think about what would happen in the circuit. The resistor restricts the flow of charged particles. The bigger your resistor, the slower the particles move. The capacitor stores those charged particles. Does it make sense to you that if I increase the resistance, it would reduce how many charged particles are flowing in the wire, and therefore it might take a longer period of time to fill up my capacitor? If I reduce the resistance, then I increase the number of charged particles that can flow in the wire, and I might be able to fill up my capacitor faster. Now, the reason I am transitioning from an uppercase Q and an uppercase I to a lowercase q and a lowercase I is because I think there's a time variance that affects how fast the charges will flow. And as I told you before, anytime we start dealing with a current or a flow of charges in which the current and charge is not constant, I'm not going to use an uppercase value to represent current and charge. I'm going to use lowercase values. This is a symbol to you that the uppercase value tends to represent the steady state condition, and the lowercase value represents the time varying condition. Meaning there's a steady state condition in which the capacitor will be fully charged. The maximum amount of charge the capacitor can hold. That is considered a steady state condition, something that the circuit will reach after the capacitor is fully charged. We tend to use uppercase Q to describe those steady state conditions. But up until that time, the capacitor's charge will be starting from 0 and changing over time until the capacitor comes to full charge. So we use a lowercase q to describe the charge as it fills the capacitor. And we'll also use a lowercase I to describe the current in the wire as the capacitor becomes full. So I'm going to rewrite this as lowercase qc minus lowercase ir. And then I'm going to immediately suggest that we look at the fact that we have a differential that can be used to replace one of the variables in this equation. Because what we have here is an equation that has charge and current, but charge and current are related. Right? Current is the flow of charged particles. If I substitute in our definition of current for the current in our circuit, I create a first-order differential equation. So question 1 I want you to be able to answer is, can you generate a differential equation whose solution could tell you how the capacitor gets charged? This would be it. This would be an equation that would determine the time in which it takes a capacitor to charge, or the charge on the capacitor as a function of time. Of course, we have to solve this differential equation. And solving a differential equation is going to take a little time. But most of you guys had mechanics already. I say most, not all, most. Which means most of you folks know a way in which we're supposed to solve differential equations. Now, if you weren't in mechanics last year, that doesn't mean you're excused from knowing how to do this. It just means that I'm going to go through the set of steps at a pace I feel is appropriate for the majority of the students in the room. But we will do this over and over and over again. So there will be lots of time for us to fill in the gaps when you miss stuff. The process we're going to use for solving this differential equation is called separation of variables. And it's not particularly hard to do. However, there are a series of steps that have to be followed and executed exactly each time. This is not necessarily taught in calculus right away. In fact, I'm not sure it's taught in BC either. You guys have had BC. Do you guys do full first-order differential equation?
We do separation of variables.
But you do separation of variables, right? Okay. So to do separation of variables, we have to first establish if there's anything about our system that we know at time 0. And we do know a couple things at time 0. First, at time 0, our capacitor is uncharged. So we know the charge on the capacitor at time 0 is 0. That's really all we know. But it's a boundary condition that we have to be aware of. So let's start with separation of variables. Step 1, you need to isolate your differential. So the differential appears in one term here, so we're going to isolate the differential by moving it over to the other side of the function. Now we can decide to leave the r here or move the r over to the other side of the function. It will make no difference in the work that we do. R is a constant. The resistor in the circuit isn't changing after we close the switch. So because it's not changing, you can leave it anywhere. We know that it's not really going to be a part of any integration we're going to do. But the next step, after we've isolated the differential, is we have to split the differential. Now our differential has two parts. It's a small change in charge over a small change in time. We're going to multiply both sides by dt to separate our differential. All good? All right. Our next step, and this step is not particularly hard, but it's one that you have to be thoughtful about. We have to collect variables. You see, we're going to be integrating both sides of this function in a few minutes. And the only way to do so is to make sure that we have the variables associated with the differential on the same side of the equation. So on the left side of the equation, we have a dq. On the right side of the equation, we have a dq, which means anytime we see a reference to q in this function, it has to be on the right side of the equation. And on the left side of the equation, we have dt. So any reference to t in this equation has to be brought to the left side of the function. Now, if you look carefully, you'll notice that we don't have t anywhere in the function, but we do have q in the function. So the only way to get q over to the other side is divide by this entire term. So that's what we're going to do. We're going to divide by that entire term and move it over to the other side of the function. Well, we now have a function that we are ready to use to set up our integrands. So once we have gotten all of our variables on the correct side of the equation and we've separated our variables correctly, we're going to integrate both sides of the function. So draw our integral symbol. And there's a couple of different methods, of course, to do this. There's doing this as an indefinite integral or doing this as a definite integral. You guys who are just starting in calculus, you probably don't know the difference yet if you're in AB. I'm not even sure you know the difference yet if you're in BC. But either way, you need to know the difference for us. Indefinite integrals means that we're going to take the integral, but we will have to, at the end, apply a constant to the function in order to apply our boundary conditions. For us, we apply the boundary conditions here by doing a definite integral. It doesn't look like a definite integral because you're going to see something we're going to do that kind of falls outside the scope of what you have learned as a definite integral. But this is how they want us to do this in AP Physics. So the bottom of both of our integrals has to be the initial conditions of our system, and they have to match. We already know what those initial conditions are. The left side is 0 for t. We're starting at time 0. The right side is the charge on the capacitor at time equals 0. Please, in your notes, don't just write that it's always going to be 0. That's not true. Just like on the left side, it's not always going to be 0 for time. We established a boundary condition. We're applying it. So the initial time, the time when the switch is closed, was 0. We said that's going to be time 0. The charge on the capacitor at time equals 0 is what goes here. Now it happens to be 0, but it won't always be. If we're discharging the capacitor, then the value we're going to put there is whatever the charge on the capacitor was at time equals 0. So remember, it's whatever your matching conditions are going to be. The top gets a placeholder. Remember, we're trying to create a function of charge related to time. So on the side that has time, we're going to put a lowercase t. It's going to be the function variable that represents t sometime in the future. On the right side, we're also going to put a function variable, lowercase q. It represents q sometime in the future. Remember, our goal is to create q as a function of t. So we are putting function variables into our integral so that at the end of this, we get q as a function of t. Now, these steps are the major steps you're expected to be able to do. The first step is creating a differential equation by substituting a differential in for one of your variables. The second step was isolating the differential, getting it to one side of the equation, so it was by itself. The next step was separating the differential. And the last step, we combined two things. We collected our variables and then set up our integral. Those are the steps that we're using here. This nets you most of the points. So if you're asked to solve a differential equation, there's probably going to be a couple of points wrapped up just in this portion of your solution. However, what we're going to do next is solve, which means we're going to do our calculus. This is only going to be worth 1 point. In fact, they're probably going to tell you what the answer is, so that they're going to say, prove that this is true, you'll get to this point, and you'll either be able to do the calculus or not. Now, the left side is going to be easy because we're going to be doing the antiderivative of 1. So since there's no variable there, I'll remind you, what's the variable that's there if there's no variable present? T to the 0 power. So yeah, it's t to the 0 power. Our antiderivative is going to be t to the 1 power divided by 1. And we'll establish this from 0 to t. The left side's not that much work. The right side, it's going to be some stuff. It's going to be some stuff. So let's do that stuff over here. Our integral from 0 to q of r over our EMF to q over c dq. First, let's take that r out. It's just a constant. It's just in the way. That'll make it a little bit simpler. But the problem here is this doesn't match one of our archetypes of integrands. So you have to use something that some of you haven't learned yet. It's called U substitution. And this is a calculus exercise. It's basically the chain rule in reverse. But that's what it is. It's what the result of the chain rule produces. We have to find something that we can substitute in that will lead us to a integratable solution. So we are actually going to substitute in for u, meaning we're going to create a variable u and use it as a substitute for other variables in our function. The variables we're going to use is the function in the denominator, because we have an archetype for that. We know that 1 over u has an antiderivative, one that we're aware of. So we're going to try and see if we can create an integral that matches one of our standard types. The problem is, if we replace epsilon minus q over c with u, we're still integrating with respect to q. So what we have to do now is take the derivative of du with respect to q. I'm sorry, we have to take the derivative of u with respect to q, so we can get a substitute for dq. So when we do that, epsilon is a constant, so it just becomes 0. However, the derivative of q over c with respect to q is just 1 over c. So we've taken the derivative of both sides. We want to solve this for dq. So I'm going to cross multiply to solve this for dq. And I'm going to get negative c du equals dq. Now the purpose of doing all of this is to have a substitute for u and a substitute for dq. So now we make our substitutes. I'll point out that negative c is a constant itself, so I can pull it out of the function. I made a mistake, and thank you for not pointing it out. I'm glad I was the one who got to pick it up. dq equals negative c du. There we go. Now, this integrand is one that is known. You may not know it, but it is one that is well known. The antiderivative of 1 over u is the natural log of u. So, and I know that I'm doing this in a non-standard way. If you are in calculus, you were taught to also change your limits when you do u sub. I'm just going to hold on to them, because I'm just going to sub back in my original function in just a minute. So I'm going to, I guess I don't need my integral symbol. I'm going to do the antiderivative of 1 over u is the natural log of u. And I still have limits, but they're with respect to Q, not with respect to U. So it's at this point that I remind you what our substitute was. And before we put our limits in, put back in our original function. Now, just a reminder, all of this equals t being evaluated from 0 to t. Now, this isn't the end, but that's all the calculus that there is. You now need to isolate this for q. How many of you know what to do here to solve this for q? Not enough of you. So you guys who don't know how to solve this for q, I will do it one time, okay? One time. And then you have to be a master. Everybody got it? Because after this is just algebra, but it's still something you need to be capable of doing. Now, we got here from doing U substitution, and there was a question about what happened here. I could probably be honest with you and say I don't always stand on, I don't always do my math as cleanly as I should, or at least as cleanly as your calculus teacher would probably like. What I did here, and I have a few more minutes now so I can be a little bit more careful. I took the derivative of both sides of the equation with respect to q. What that looks like is d dq of u, d dq of everything inside here. And I wasn't specific. I wasn't careful. I just did it real fast. The derivative is distributable. You can distribute the derivative. It's like any other function or any other number. Well, not number, it's a function. When I did that, the first one, it's how does the voltage supply change with respect to the charge? It doesn't. We believe in an ideal voltage supply that provides the same potential difference regardless of how much charge is being produced. So that's 0. It does not change with respect to the charge. C also does not change with respect to the charge. It's the capacitance. It's a physical property of the device. As it is a constant, it passes outwards, outside the derivative. So now I am taking the derivative of q with respect to q. This is a polynomial. So it's q to the 1 power. I use the polynomial rule for derivatives, which is take the exponent, bring the exponent down to the front of your variable, then subtract 1 from the exponent. So this becomes, using the polynomial rule, 1 times q to the 1 minus 1. Well, q to the 1 minus 1 is q to the 0, which makes this just 1 times 1. Good enough? So that's why this became negative 1 over c. And that equals du dq. That's where it came from. So for those of you who don't know that, getting back to the algebra, the last step of completing an integral is to put your limits in, which we had not done. The left side, you put the top limit in first, then you subtract when putting the bottom limit in. So this is just going to be t minus 0. On the other side, put the top limit in, which is just q. But subtract and put the bottom limit in. When I put the bottom limit in, which is 0, it zeroes out this term. So this is just going to be the EMF. Okay, so now we've completed all the calculus part and we're into the algebra. You want to try and simplify. So we want to get q by itself. We have to tease it out of that natural log. So we will. I will divide by RC first. And I'll combine the natural log into a single function. That good for you guys? I can now raise both sides to a base of e. I went ahead and distributed the EMF to both terms. I want to get Q by itself, so I'm going to negotiate a little algebra. And now I'll multiply by what's in the denominator of that fraction. And if you pay very close attention, you'll know what the next step is. This represents the full charge on the capacitor, right? Maybe a max might be nice to put there to recognize this would be the full charge on the capacitor. So Q as a function of T equals Q max 1 minus e to the negative t over RC, where Q max is your voltage supply times your capacitance. Do you know what this function looks like? Sketch it. You have access to Desmos, you have access to a TI, sketch it. But before you, if you don't know, think about it, work it out in your head what it is. What is, when t is 0, this is e to the 0 power. E to the 0 power is 1. 1 minus 1 is? So at time equals 0, a boundary condition, our charge is 0. Now consider what this function does after a long period of time. When t is a very big number, what is this term? It approaches 0, doesn't it? Because when t is a very big number, that's going to be e to a big number, but it's a negative, so it's 1 over e to a very big number, right? That means 1 over a big number, which makes it 0. So as Q goes to infinity, this becomes Q max. So you now know 2 points. You know time 0 and time very long, very much in the future. Is it concave up or concave down? How do you think it would be? Do you think the function would approach the max as if it's going to infinity, concave up? Or approach the max as if it's leveling off, concave down? So you should be able to imagine what this function is doing without having to plot it, but you should plot it in Desmos. So if I want to plot Q, I know at time 0 it's 0, and I know that after a long time it's going to reach its maximum. This is an asymptotic function. And you should know how to model it in either your calculator or Desmos. Function isn't what we just saw because we can't see the capacitor charging. But if you take the derivative of this function with respect to time, you should get the current function. Do so, please. That should be something that's in your wheelhouse. You've had Calc AB. Most of you are you're just getting into the integral part, means you've done this derivative. So take the derivative with respect to t. What you get should be an obvious answer. So ask your question again.
What is the difference between current and charge?
Current is the flow of charged particles. Right. So our capacitor has static charge building up on the plates. But passing through the resistor is the current. That's a flow of charged particles through the resistor. So when we took the derivative of the charge here, we're taking the derivative of the charge as it builds up on the capacitor. But that has to be the flow of the charged particles into the capacitor or out of the capacitor, depending on which plate you're talking about, which has to be the same in this loop of circuit. So what we're looking at is the current as it goes into or out of the capacitor. But since the resistor is in series with the capacitor, this also has to be the flow of charged particles as a function of time through the resistor. Right? V equals IR, correct? So, because we're not done yet, the voltage across the resistor would be R times I as a function of T. So the voltage across the resistor isn't constant. The voltage across the resistor is changing. So if I sub in what we have, you'll have I max times R e to the negative t over RC. Correct? But I max times R is the EMF of your circuit. Correct? Because understand what I'm saying. I need you to, because what I'm going to say next is very important. Probably the most important thing I'm going to say today. Which probably means the bell's about to ring. So I'm going to rewrite this one more time. But again, this is the voltage across the resistor. I probably should do this just to make sure I'm driving it home. It is a function of T. Now, listen closely. The voltage across the resistor at time 0 is the entire voltage applied to the circuit. It is the EMF of the battery, which means there's no voltage across the capacitor because of Kirchhoff's rules. So, by extension, VC at time 0 is 0. The capacitor behaves as if it has 0 resistance at time 0. You have to understand, a capacitor in this circumstance is acting like a variable resistor, changing. At time 0, the resistance of a capacitor in this circumstance is 0. So a capacitor with no charge on it acts as though it has a resistance of 0 in the circuit. Now obviously, maybe not obviously, after a long time has passed, the voltage across the resistor is going to be 0, right? That means the voltage across the capacitor has to be whatever the voltage of the battery is. Has to be, right? They're changing places. When you connect that circuit, the voltage is all across the resistor, none across the capacitor. And then as the capacitor charges, the voltage across the capacitor is increasing at the expense of the voltage across the resistor decreasing. Until you reach this steady state condition, where the voltage across the capacitor becomes the voltage of your power supply. That also suggests that the resistance of the capacitor at an infinite timeline is infinity. No charge is passing across the capacitor. Right? It's all in the circuit. Now, all the stuff you have you should have all this in your notes, right? We just all wrote it out. This is the current passing through the circuit. This is the voltage across the resistor as a function of T, right? It all came from that charging equation from up here when we did the charge on the capacitor. Right, but you have to understand, this is the basic stuff of how an RC circuit works. Notice in all of these time variant things, in all of them, right, you see that, don't you? This part, RC, is the timing part of the circuit. It determines how long this takes to happen. Do you see why that has to be true? If R gets bigger, this takes longer to happen because the denominator of that fraction gets bigger. So changes in T don't express themselves as fast because the denominator is bigger. If C is bigger, this takes longer to happen. you can control, you can tune your circuit to decide how long this takes by changing the capacitance or the resistance. And it's not that hard to think about. If you go all the way back to when this started, this measly little circuit, this is a fixed value. Right? Obviously, it does not contribute, or it doesn't appear to contribute, to how fast the circuit charges or discharges. It's about physical parameters of the circuit, the resistance and the capacitance. You make the capacitor bigger. You make your bucket that stores charge bigger. It can take more charge, so it takes longer to fill it up. If you make the resistance bigger, it's like turning the hose slightly off. Less charge is flowing into the capacitor, so it takes longer to fill it up. Do you guys see how that's working?